Okay, with the server running at the background, I'm going to use the only debugger to uh, debug um, the PCman server. So this is the procedure. This is only DB debugger. It's open right now. All I do is go to File. File, attach, and then search for the program, search for PCman. So this is PCman here, the server that is vulnerable, and click attach. So once we attach, this is the output that we get. You can see right here on the right hand side is the registers. On the left hand side, so down below here we see the program is paused. See red in red, on yellow says paused. So this is PCman loaded in only debugger. So once this is loaded, we press F9. Press F9 and then it starts running. Once you hit F9, the program starts running. Okay, so it continues until the program crashes, until PCman software crashes. So when it crashes, so like I said earlier, we open only debugger. See on the right hand side the register. On the top left hand center of the screen is the assembly instructions being executed by the program. The bottom left is the memory, while the bottom right is the stack. And we notice that the program was in pause until we hit F9. So once we hit F9, the program starts running. And then we run the fuzzer again, the code that is written in Python. And then once it crashes, we won't close the program. Once there's a crash, we notice only the debugger goes to pause again. And the register values will be frozen on the values they were at the time of the crash. So this is the register values that we get at the time of crash. So looking closely at this, we can see that the EIP register value is now 4141414141. Right there, we can see the EIP register value. And what does that mean? In hexadecimal, it means A, which is the string we were sending in our fuzzer. So EIP has been written at this point, has been overwritten at this point with AAA, meaning the program went to try and execute the memory address 0 by 41414141. Because this isn't valid, because it isn't valid, then it crashed. So now controlling the EIP. Now it means we can control the EIP. Because we need to precisely overwrite 4 bytes in the EIP, it is required for us to understand which 4 A's out of the 2100 A's we did the overwriting. A tool called pattern created from Metasploit can help us to do this, to control EIP. It creates a unique string that, when matched with its other tool called pattern offset, will be able to identify the 4 bytes that is overwritten on EIP. So this is the code written with Metasploit to help us to control EIP. So using the pattern create tool, a string of 2100 bytes is created. We then place the string on our exploit and send this to the server instead of our variable length payload. So this is the code that we wrote in finding the EIP offset. So this code is also explained step by step. We put some explanation on every line to explain how to find EIP offset. So again, we restart only debugger and the server, and we attach only debugger. We press F9 to run the program. We run the Python again, and once again it will crash the server. Only debugger should pause once it crashes and the value of EIP examined. This time around we found to have the value of 0 by 43386F43, which is right here. EIP 43386F43. So that's the unique string that was sent. So the sister tool pattern offset is used to determine exactly how many bytes along 43386F43 address is. So this is the pattern offset. You can see it right here. To determine how many bytes along that address was sent. So eventually the exact match at offset is 2004. It is now known that 2004 bytes occur before EIP is overwritten. So at this point, this is how much you can explain. Too much of everything is not good. Okay?